Now we're going to go over atomic mass and atomic mass units. Atomic mass unit, basically, think about, I believe we went over this in chapter 1. Most of the mass is in your nucleus. The electrons weigh pretty much nothing, so we don't consider those really in the mass. So an atomic mass unit is basically how many protons and neutrons you have. So an AMU, or atomic mass unit, 1 proton equals 1 and 1 neutron equals to 1. So we could look at carbon, for example. Carbon has, if we look on the periodic table here, 6 protons, and though it doesn't show it on here, it has 6 electrons. I'm not sorry, well, it does have 6 electrons, but 6 neutrons, okay? So if we add that together, and come over here, carbon, oops, let me change this, layer it, let's try pink, actually let's try this pink, okay. Carbon equals to 12 protons plus 12, oops, that does not look like a 12 neutrons. So if we add that together, and I don't know why I'm saying 12, it's 6, ignore me, 6 protons, I'm just getting ahead of myself on the math, 6 neutrons, so when we add that together, that would be 12 atomic mass units. Okay, so it equals to 12 AMU. But let's look at the periodic table. It says 12.011. So not exactly 12. So what's the difference there? Well, this is actually the average atomic mass unit. Okay? So if I come back to the slide here, we have to consider all the isotopes. Remember, isotopes are, you have the same number of protons, so you're still, for example, a carbon atom, but you have a different number of neutrons, okay? And we have to look at the percent abundance on the Earth, okay? So if we look here, we have carbon 12, carbon 13, and carbon 14. Now if we just look at the weight here, what do you think we have more of? Carbon 12, carbon 13, or carbon 14? Well, if you look at the mass, it's pretty much 12, so that tells us it's pretty much all 12. Now, if the weight of carbon was closer to 13, then that tells us we have more 13 that's abundant on Earth. Okay? But how it is, it's actually about 99.9% 12 and, 0.8% 13. Or 0.08% 13, and maybe 0.02% 14. Okay, so when we average all the isotopes together, okay, because if we have carbon 13, that means we have 1 additional neutron. Carbon 14 means we have 1 additional neutron. So if I come back over here, this is the calculation for carbon 12. But if we look at carbon 13, put 13 up here. This is 12. Okay, we would have still 6 protons because that's what makes up a carbon. But this time we would have 7 neutrons. So the atomic mass unit then would be 13 AMU. And if we look at carbon 14, okay, we still have 6 protons. Oops, not plus. And then we have 8 neutrons now. So it'd be 14 AMU, okay? But if this was about, well, let's just make it easier. Let's say 99% of this, 99% of the carbon on Earth is carbon 12. And let's say we have 0.8% carbon 13 and 0.2% carbon 14. Together that's 100%. So when we average it with the weights, so we can't just say, oh, 12 plus 13 plus 14, add them together, divide by 3, because that means they all have the same amount of abundance on Earth, okay? But if we do carbon 12 multiplied by 99%, carbon-13 multiplied by 8%, carbon-14 multiplied by 12%. Add those together, and that'll give you the percent abundance. And that's the mass you actually see on the periodic table. So let's look at this example we have here. Copper has two isotopes, copper 63 and copper 6, which weighs 62.9396, and copper 69.17% abundant, and then carbon 65, which is 64.9278. That's the weight, and the abundance is 30.83%. Okay, so let's write this down. We have carbon 63, or copper 63. Copper 63. C for copper 63. And it actually weighs, what was it, 62.9396. Okay, and its percent abundance, let me see, is, let me just minimize this so I can just pull it back and forth. Is 69.17. So instead of writing it as a percent, I'm going to go ahead and write it as a decimal, which would be 0.6917. That's just dividing by 100. Then we also have copper. What was the other copper? Let's see. Copper 65, and it weighs 64.9297. Copper 65. It weighs 64. I think it was 9297. And that percent is 30.83. So you would write as 0.3083. Okay, so let's multiply these numbers out, and then we add them. So right here we do 69.17 times 62.9396, which is what we have right here, and then we're going to add this 64.9297 times 0.3038. So we're going to multiply these out and then add them. So if I put that out, multiply these, add these, and I have the answer right here when you do it. You should get 63.55. 63.55 AMU. Now let's look at this, okay? Now, if we see that about 69% of it was carbon 63, or copper 63, and 30% of it was copper 65. So that means the majority of it was copper 63. And you see here that the average of them is 63.55, meaning that most of the copper is carbon 63. Though we do have a little bit of carbon 65, 30% of it actually. And so that's what changes it. So we don't see the number on the periodic table is not copper 63. It's actually 63.55 because on this Earth, 30% of the copper is 65. Weighs 65 because it has two additional neutrons. Okay? So that's how you do it. That's atomic mass unit. If you're just looking at the units, that's basically just saying a proton equals 1, a neutron equals 1, add those together, and that gives you the approximate mass. But whenever you want the average atomic mass, that's when you're averaging all of the isotopes together multiplied by their percent abundance. Okay, remember you had to multiply by the percent abundance, and not just add them and divide them. So if we go on to the next thing, the molar mass. So what is a molar mass? Well, it's pretty simple. The molar mass is actually equal to 1 AMU. Okay, so this AMU right here, so 63.55 AMU equals to 63.55, and the molar mass we say is grams per mole. So if we have, this is copper, 1 mole of copper, this is what it says, 1 mole, so per 1 mole, which is, Avogadro's numbers of atoms, it would weigh 63.55 grams. Okay, so this a molar mass tells you how much 1 mole weighs. So 1 AMU equals to 1, we'll say, gram per mole. Okay, so that's why 63.55 equals to 63.55. It's a 1-to-1 ratio. And so this tells you how much the weight of something, you literally put it on a scale and weigh it. Weight, and we'll say that, and that's in grams per 1 mole. Okay? And so that's what we usually use. Molecular weight is what it's called, which is grams per mole, because that's how we're going to do all of our unit conversions. So if we look on here, we say the molecular weight of carbon is 12.01 grams per mole. For nitrogen, it's 14.00674 grams per mole, or approximately 14. A lot of these you can, just do an approximation. Oxygen weighs approximately 16 grams per mole. Fluorine weighs approximately 19. So that tells you how much 1 mole of that atom weighs. And the next slide gets more into a mole. So let me just really quickly just tell you, and then we'll go over it again in the next one. Basically, it's the amount of mass, weight, grams, in 6.022 times 10 to the 23rd atoms of a given element. Okay? That's Avogadro's number. So that's similar to saying, 12 eggs equals a dozen. Okay? So 1 mole equals to 6.022 times 10 to the 23rd atoms. Okay? Right here. That's how much a mole means. Now, we don't want to keep saying 6.022 times 10 to the 23rd atoms. That's a huge number, it doesn't mean anything. So instead of keep saying that over and over again, we just say that's 1 mole. Okay? And this number here, Avogadro's number, is based on how many particles in 12 grams of carbon. Okay? So they literally, the scientists back in the day, they got 12 grams of carbon, okay, just like regular black carbon that you think of, and, weighed 12 grams of it, and they were able to calculate how many atoms were in that. Okay? So literally, we get carbon, and we weigh out exactly 12 grams of it on a scale. And then from there, we figure out how many atoms is in that. Okay? And when you calculate that, that is 6.022 times 10 to the 23rd. Okay? And again, we don't want to keep saying that number, so we say that's 1 mole. So when we're looking at the molecular weight or the molecular mass of something, we're looking at the weight per mole. Okay? So if we... No, it's ions trans. Sorry, what's the wrong one? So the weight is the weight of 1 mole. So if we come back over here, if we have Avogadro's number, 6.022 times 10 to the 23rd atoms, okay, we weigh out, or we actually count out, like 1, 2, 3, 4. We count out that many atoms of sulfur, and we weighed that amount of number, or that number of sulfur atoms, they're going to weigh 32.066. If we do that for oxygen, they will weigh about 16 grams. Okay, so when we're looking at the molecular mass of something, a gram per mole, we're basically saying how much does 1 mole, which is 6.022 times 10 to the 23rd atoms, that many atoms, or 1 mole of it, how much does that weigh on a scale? Okay, why do you think oxygen weighs more than nitrogen? Why are we getting different weights? Well, it's because they have a different number of protons and neutrons in them, right? Oxygen has, look at this, just look at the number here, 8 protons. Nitrogen has 7 protons. So doesn't it make sense they're going to weigh a different amount because they have more protons and neutrons in them, okay? So again, a molecular weight is just, if we weighed out 6.022 times 10 to the 23rd atoms, we weighed that out of a certain atom, like oxygen, if we weighed that on a scale, it tells us the grams, how much it weighs in grams, which in this case is about 16. Okay, so looking on here, let's look at bromine. About how much would bromine weigh? If I had 1 mole of bromine, or Avogadro's number of atoms, which is 6.022 times 10 to the 23rd, how much would that weigh? If you look on here, it would weigh about 80 grams. Okay, so I hope this helps clarify what a gram per mole is. So you could say, about 16 AMUs, or you could say 16 grams per mole. It means the same thing, essentially, because the unit conversion is the same. We use grams per mole more often, only because we can use that in a stoichiometry conversion. A stoichiometry conversion, let me say, it's just a unit conversion for chemistry, like going from a millimeter to a meter. Anyway, so it's just one to use for chemistry.